Hello, we're now in the next section, which it kind of jumps on the last section, although we're kind of picking and choosing what we want to talk about. In the previous section, we were talking about what happens if I raise a binomial to a power. You know, can I predict the terms that are going to come out of it instead of multiplying it all out tediously? Though this section, it grabs a piece of that. Remember that there was this n choose k idea thing, that the first objective that we talked about? So this just grabs onto that, the n choose k, and shows where it could be useful in other avenues of math. So and it becomes useful in probability. So that's kind of what we're gearing up towards. The next section after this, we'll talk about probability. But we just kind of want to get ready for it by talking about counting principles, permutations, and combinations. So let's see. And I forgot to mention in the previous section, if you want to calculate n choose k, remember I said, if you have a TI-30 or some kind of Texas Instruments calculator, these are the buttons you press. But if you don't have Texas Instruments, you have another brand, or you have a TI-84, so a higher level Texas Instruments, some kind of calculator that I didn't mention, you can always, if you want to know how to do this on your calculator, you can Google or search whatever on the internet. Google, let's see, how about permutations and combinations and then specify your type of calculator, whatever. For example, if you had a TI-84 or something, or, a Canon, blah, 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 I don't know what brand, then specify your calculator, brand and type. TI is Texas Instruments, 84 is the type. And then you should get a page where someone's already made either a YouTube video to show you, or they show you step by step. That's probably the best way to find stuff like how to do things on your calculator. But anyway, that's how I figure things out anyway. But this section, it's counting principles, permutations, and combinations. We're kind of more focused on, we said that the n choose k was like, how many ways can I choose k items out of n? We're going to more focus on that idea where I want to count things. How many ways are there to do this or do that? So kind of interesting. But the first one, we're going to use what they call the fundamental principle of counting, or the fundamental counting principle, which just kind of shows if you have a bunch of choices to make, like in this first example, what do they say? Let's see. It says a pizza can be ordered with 3 choices of size. Okay, so there's one choice, either a small, medium, or large, and then 4 choices of crust. Oh my God, I'm already confused. Thin, thick, crispy, or regular. I don't know. And then 6 choices of toppings. You got ground beef, sausage, pepperoni, bacon, mushrooms, onions. All right. How many different one-topping pizzas can be ordered? Holy crap. I imagine there's going to be a lot, right? So what you end up doing is you think of, okay, how many choices are there for what was the first choice we had to make? The size of the pizza. How many choices for size? There was small, medium, and large, so 3 choices. And then you ask yourself, okay, how many choices for the next choice we were supposed to make? What was it? Types of crust. So there are 4 types of crust. Okay, 4. And then the last choice we had to make was how many toppings are there? How many choices of topping? So the last was size, crust. Oh my God, my handwriting is terrible. Crust. Size, crust, and topping. Well, there were 3, 4, and 6 choices for each of those. And so if you have 3 choices to make and you want to know how many total choices are there, you multiply the number of choices for each choice, I guess. Yeah, you multiply to find the total. To find the total number of choices. And that goes for anything in real life. If you have a few choices to make and you want to know, wow, how many outcomes were there for those 3 choices? Well, think about all the outcomes there were for the first choice, how many outcomes were there for the second choice, for the third choice, and then multiply them together. So that's what they did here. They said, well, there are 3 sizes, there are 4 types of crust, there are 6 toppings, and then multiply those together and I'll get 72 total. So there are 72 options for the different size, different pizzas. And that's only for one topping. Imagine if you could do any number of toppings. Holy crap. That'd be a lot of options. So with that in mind, let's try this next one. They said, An ice cream store sells 2 drinks. Okay, you can either get a soda or milkshake. Okay. And then 4 sizes. Okay, holy crap. Small, medium, large, or jumbo. And then 5 flavors. Vanilla, strawberry, chocolate, coffee, pistachio. And how many ways can a customer order a drink? So what, kind of like we did in the previous one, I have to have a space for the first choice. How many choices were there for, what was the first choice? Type of drink, I guess. How many types of drinks? Because they said there were sodas or, what else? Oh, milkshakes. So I'm going to put a 2 there because I know there were 2 choices for that. And then I think about the next choice. What was that? It was, oh, size. So that would go here. How many sizes are there? Many sizes. Well, they say 4 sizes? Yeah, small, medium, large, jumbo. Okay. And I think there was only one more choice to make. It was how many flavors are there? And there were, how many? 5 flavors. So 5. A number of flavors. How many flavors? And of course, you don't have to write this out every time. You can just show, like to show your work, you can just go, oh, 2 times 4 times 5 is blah. You know, that's all you have to do. But you'd end up with a 40. So there are 40 total choices here. If you were to, you know, make those 3 smaller choices back to back, you'd have 40 total options. That's a lot. 40 outcomes. That's interesting. All right, let's try this next one. The license plates in a particular state display 2 letters. Okay, so let me think about this. The first 2 are going to be letters. So this is a letter, and this is a letter. Okay. So I mean, just to get ahead of myself, maybe there are 26 choices, right? Because there are 26 letters of our alphabet. 26 choices. Did I spell choices with the S earlier? Oh, Lord. Good thing I'm not an English teacher, huh? Wait, does choice have a C or an S? Oh, well, who gives a crap? Am I right? Am I right? Nobody cares. Okay. 2 letters, we got that. And then followed by 3 numbers. So, and then I think they mean 1-digit numbers. So I wouldn't think that one of those numbers could be a 10 or 11. It's 3 numbers, they're each 1 digit. So there are going to be 3 of them next to each other. This is a number. You know, so is this, so is this. And I'm imagining it's from 0. It's either a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Nothing bigger than that, because then it would all of a sudden become kind of like 2 numbers or 2 digits or something like that. So, okay, they want to know how many different license plates can be manufactured. Well, just like we saw in the previous one, and it kind of gives us a hint here to describe it, you want to multiply the number of choices for each of the letters and each of the digits. So we said the very leftmost is supposed to be a letter. There are 26 choices for that guy. And the next one's a letter. Same thing. There are 26 choices. But the third guy is supposed to be a digit or a number. But there are, let's see, from 0 to 9, I would think 9, but there are actually 10 choices because 0 counts as well. From 1 to 9, that's 9 choices, but if you add 0 to the mix, there's 10 choices. And all 3 of these guys are supposed to be digits, so there's 10 choices for each of them. Holy shamoly, that's going to be a big number. 26 times 26 times 10 times 10 times 10. Holy shamoly. That's, oops, why'd I put a 2? What the hell? 676,000. Holy moly. That's kind of interesting, right? If you want to know how many possible license plates are there. That is a lot. It doesn't seem like there should be that many, huh? I don't know. Maybe I think too far into it. Plates. That is a whole lot. All right, I think this is the last one before the next objective. You are taking a multiple choice test that has 5 questions. Each of the questions has 3 answer choices with 1 correct answer per question. If you select one of these 3 choices for each question and leave nothing blank, in how many ways can you answer the question? Holy crap. Well, let's see, there are 5 questions, so it's kind of like I have 5 choices. 1 for each of the questions. There's 3, 4, 5. All right, but each of them only has 3 choices, right? First question has 3 options. Second question has 3 options. Third question, fourth question, fifth question. I think it ends up being just 3 multiplied by itself 5 times, which would be 243. Is that right? 3 to the 5th? Yeah, okay, just making sure. So that's a lot of outcomes, huh? Wow. Yeah, that's interesting. I think if you're thinking, man, that doesn't make sense, that's too many, you're probably on the right track. Because a lot of these, you end up with I don't know, a number that seems like it's way too big. It's kind of weird. All right, well, that was pretty interesting. Now we're on to the next objective, which is more counting, I guess. Let's see. Counting things that are hard to I mean, this is a more difficult counting principle, I guess, is what I'd say. So let's see. We've seen this guy before, the number of combinations of n things taken r at a time. Or in other words, the number of ways there are to choose... Let's see. We used a k, before. The number of ways there are to choose k items out of n. So we've seen this little formula before. That guy. But this one we haven't seen. So that's going to be a big difference. But either way, what you're doing is you're choosing r out of n items. So they sound like they're going to be the same formula, but they're a little different. And then over here to the right, it kind of describes when you would use one or the other. But let's see, your calculator should have both of those functions. Calculator should be able to calculate either of those. So you shouldn't have to do either of those by hand. Calculate the number of permutations of r out of n things, or the number of combinations of r out of n things. So all you have to do is decide, in a certain problem, which of these am I supposed to choose, and then use your calculator to calculate it. But the question is, which one, in which situation do I choose one to calculate, and which situation do I choose the other? But this should answer the question. So let's see, a combination, it says on the left, is an arrangement of items in which order does not matter. And then a permutation, it's an arrangement of items in which they have to be in a particular order, and order matters. And that, right now it might not make much sense, but I think when you see the examples, you'll kind of know what they mean by order. So that's the only thing we have to do is figure out, does order matter in all these, and then we'll know which of those to use. Does order matter? That's our first question. Let me read this question and think about it. A corporation has 7 members on its board of directors. In how many different ways can it elect a president, a vice president, a secretary, and a treasurer? So it looks like I'm choosing, it's either going to be, there are 7 members, so it's either going to be 7 choose 4, or 7 permutations of 4. Because we said there are 7 members, that means n is 7, and I'm choosing a president, a vice president, a secretary, and a treasurer. That's 4 people. I'm choosing 4 people out of 7. So it's going to be either the combination or the permutation. Do you think if I chose those 4 people, would the order that I choose them in matter? Well, in this case, I'd say yes, it does, because if I choose them in one order and then I mix them up and choose them in a different order, they're going to have different jobs. Because if I choose, let's say, Joe for president, and then Jimmy, I don't know, I'm making these stupid names up, for vice president, and then Sally, of course you got to choose names that your grandpa and grandma might have, and then I don't know, what's another grandma name? I don't know, whatever. How about Jill? I don't know. Whatever. So at first, if I chose those 4 people in that order, they'd have those jobs. But if I chose the same 4 people, but in a different order, they'd have different jobs. So this time I'd say yes. Because they'd have different jobs, if you choose them in a different order. Okay, and then that narrows it down, because that means we have to use permutations, not combinations, because that's what it said over here. A combination is where order does not matter. A permutation, order does matter. So that's how I know I'm using permutations, and I can use a calculator. Calculator. And like I said, if you don't know how to use the particular calculator you have, you should Google how to calculate permutations on a TI-84, or on a Canon whatever the name of it is. But on a TI 30X, that's what I have, or a 32, or anything in the 30s, you should be able to press, whatever n is, 7, and then I choose the PRB button, which it's supposed to bring me to probability. And then I scroll over to NPR, and I press enter on that so that I select it. And at this point, you should see on your calculator screen 7 NPR, and then you have to specify what R is for. And then once you type that, you should see 7 NPR4, and then you press enter, and that should calculate it for you. So let me see here. 7 NPR4 gives me 840. So there are 840. That seems like way too many, right? There are only 7 people on the board, and I want to choose 4 of them for jobs, but there are 840 ways to do that. What the hell? But I think it's because order matters. So there's a lot more options when order does matter than there would be if order didn't matter. All right, I think we're getting the hang of this, hopefully. Let's try this next one. It says, using 15 flavors of ice cream, how many cones with 3 different flavors? Okay, so I can already see, before I even think too far into this, I'm choosing 3 out of 15. So it's either going to be the combinations or the permutations of 3 items out of 15. But I have to figure out if order does matter. How many cones with 3 different flavors can you create if it is not important to you which flavor goes on top, middle, or bottom? Okay, so clearly they've really spelled it out for us. Order does not matter. Does not matter. But if you're like me and you're very serious about your ice cream, order would matter, you know? You gotta have the vanilla before you have the chocolate and before you have the strawberry. And, you know, there's a very specific thing going on here. But no, I guess this person doesn't care. They just love chaos, I guess, whatever. But we know when order does when order does not matter, we use combinations. Permutations we don't use today because, not today, but, you know, in this example, because you only use those when order does matter. In this case, order does not matter. So I'm just going to use my calculator. On the calculator, I'll type in 15 and then look for the PRB button. And again, this is specific to this type of calculator. If you have a different type of calculator, the beautiful internet should probably tell you what buttons to press, but it's probably something similar to this. And then enter, and then I'm going to do the second number 3, and then enter again, and then I should see the answer on my screen. Let me see. I want to do 15, choose 3. That'll be 455 is what I get. That seems crazy. There are 455 different ways you can get 3 scoops on a cone. If there are 15 options, what the hell? Yeah. I don't know. I almost don't believe these answers sometimes, but it's true. And how many ways can 6 cookbooks be lined up along a shelf? That's kind of a confusing one. So I guess when I do that, what am I choosing? Well, there's 6 cookbooks. So it's going to be 6 choose something or 6 permutations of something. I don't know what. But how many of you choosing? I think you're choosing all 6. Because, you know, there's 6, let's say there's 6 cookbooks on your counter at home, on the counter in the kitchen. You want to take all 6 of them and arrange them in whatever order you want. So you're really taking 6 out of 6 items. So that's kind of a weird one, but you ask yourself, does order matter? I think the way that they phrased it, in how many ways can 6 cookbooks be lined up on a shelf? It sounds like the way they phrase it, order does matter. Because I think different arrangements are different to them. And different arrangements mean different order. Order does matter just based on this because, yeah, I would say different order means different, well, I guess to use their phraseology or whatever, different lined up versions, I don't know, whatever, of it. So I would say since order does matter, I don't want to use the combinations, I want to use permutations. So I can do that on my calculator. I'm going to do 6 permutations of 6. So I press the 6 button, and then PRB, grab the NPR, and then the rightmost number is 6. I get 720. Holy shnikes. Whew, that's crazy, huh? That's a lot of ways, but hey, what are you going to do? And you know, you'll get more into this in the future, but kind of this is what's going on in the background is, to me it's interesting. I like this stuff, probability and combinations and permutations. Let's say, so there are 6 books, okay, then there's 1 book goes on the left, 1 book goes next to it, 2, 3, 4, 5, 6, okay. So if I use that counting principle from the first objective, I think how many choices are there for the first book? I mean, like I say first, but the leftmost. So the leftmost book, I can choose any of the 6. So there are 6 choices there, number of choices. But once I put a book there, how many choices are there for the second book? Well, there's already 1 used that's sitting on the left, so there's only 5 choices now. There's 1 less than there was before. And now that there are 2 books already sitting on the shelf, there are only 4 to choose from for the third one. And you can kind of see where this is going. Now that there are 3 of the 6 books are already sitting on the shelf, there's only 3 left to choose from for this 4th book here from the left. And now there are only 2 books to choose from. Once 5 of the 6 books are already on the shelf, there's only 1 left to choose from. So you're multiplying all these together, which would, you know, if you look at it that way, it's 6 factorial, which is 720. So that's the idea behind it. Anyway, it's kind of, I think it's interesting, but I'm weird. I like math. I'm a weirdo. Let's try this other one. We got, out of a class of 22, how many different groups of 7 students can an elementary school teacher select? Well, let's see. It's either permutations of 7 students out of 22 or combinations of 7 students out of 22. I just have to figure out, does order matter? Let me see. The class has 22. How many different groups of 7 students? I'd just say, based on the way they phrase it and the information I'm given, I think order does not matter. It does not matter. Only because they said, how many groups of 7 students can I get? Well, it's not like they said they have specific jobs or they have to sit in a specific place. You know, I think like if you choose Sally first or Sally third or fifth or seventh, it doesn't really matter. She's still in that group of 7 either way. So I don't think it matters the order. That means I don't want permutations, I want combinations. So I'll just use my calculator to calculate that guy. It's about, no, not about, exactly, let me see here. 22 PRB. Okay, I choose the NCR, and then I want 7 as my second number. Holy moly! 170,544. I guarantee you're going to do some of these on your homework or quiz and say, what the hell, that number's way too big. Let me try that again. And that's, and then you get the same thing again, and it's just because there's just a lot of combinations that you wouldn't think there'd be that many, huh? But there are. It's crazy. All right, let's try this one. In a race in which there are 50 runners and no ties, in how many ways can the first 3 finishers come in? Okay. So it sounds like I'm choosing out of 50 people. I'm choosing 3 for the first 3 finishers or whatever. So it's either combinations of 3 out of 50 or permutations of 3 out of 50. But I think in this one, at first I might say order doesn't matter, but I think order does matter. You know, because in a race, you either become in first, second, or third. You know, and I think that it would matter to the people that come in first, second, or third, whether they come in first, second, or third. Nice. You're first, second, third, you know, or you didn't qualify. And that does matter to people, I think. They really care about where they ended up. So since order does matter, I don't want combinations, I want permutations. Let me see. So I'm going to calculate that on my calculator. 50 permutations. Well, 3 permutations out of 50 people are going to give me 117,600. Holy crap. That's a lot. Okay, let's try this next one. How many different 4-letter passwords can be formed from the letters? Okay, how many letters are there here? A, B, C, D, E, F, G. 1, 2, 3, 4, 5, 6, 7. That's 7 letters. So I'm choosing 4 out of 7. So it's either going to be combinations of 4 out of 7 or permutations of 4 out of 7. I just got to determine whether order matters. Okay, how many different 4-letter passwords can be formed if no repetition of letters is allowed? Okay. Well, does order matter in a password? I'd say yes. Probably, right? Like if, you know, let's say the letters I chose are, you know, A, B, C, D, just to make it simple. Well, what if I mix those up? I write C, A, D, B. Well, those would be different passwords, right? So that's my idea here. Order matters because you get a different password. These are, even though they're the same letters, so I'm choosing the same 4 letters out of the 7, they're different passwords because they're in different order. So I'd say yes, order matters. This guy's not the one I want. I want permutations because that's where order matters. Order matters with passwords. Hello. So I'm going to calculate that on my calculator. What's 4 permutations out of 7? Let me see here. It would be 840. That's pretty serious. So that's only if you're choosing out of 7 letters. So imagine, you know, when you make a password on the computer, there's 26 letters you could be choosing. And there are, 10 digits you could choose anywhere in there. Plus all the characters, the ampersand, the @ symbol, all that crap. There are a lot of possible passwords out there. Holy moly. All right, anyway. So I think this, you know, there are only 2 objectives in this section. We're just kind of trying to do a lot of examples because the more of these you see, the better you'll be at them and the more, you know, it'll be more easy to understand. I think these problems, the hardest part is figuring out whether order matters or not based on the context. Sometimes I'm wrong, you know, I have to really think about it. Let's see, in this second to the last problem here, how many different 4-card hands can be dealt from a deck that has 16 different cards? So, okay, I think you're either going to be choosing 4 out of 16 with combinations, or you want 4 out of 16 permutations. Let's see. So if you've ever played cards, you know, with the king, queen, jack, 10, 9, 8, da-da-da, and ace and all that crap, I don't know, I guess if you're not familiar with cards, then these problems are kind of tough when they talk about cards. But usually if you're dealt a hand of cards, in this case you're dealt 4 cards out of 16, imagine you have 4 cards in your hand, or like 4 small pieces of paper or whatever. Does it really matter what order you got them in? Not really, because you can take the 4 that are in your hand and switch them around if you wanted to, and then it wouldn't be different. It'd be the same hand of cards. So I'd say order does not matter with cards. Matter. I mean, when you're initially dealt a hand, that means I don't want permutations, I want combinations. Yeah, because like I said, you're given 4 cards. That's fine. You're given those 4 cards in a certain order, but you can always rearrange them in a different order. So it's not like that would give you a new hand of cards. You'd have still the same cards. Anyway, you get 1,820. Holy crap, that's a lot. Man. Interesting. Well, okay, let's do this very last one, and then we'll move on to the last section that we're interested in here. It's the probability section, which is one of my favorites. I like probability. It's interesting. It applies to real life. Let's see, this one, you volunteer to help drive children at a charity event to the zoo, but you can only fit 8 of the 17 children. All right, hold on, stop right there. I'm going to get ready here. I'm choosing 8 out of 17, either combinations or permutations. P. Okay, one of those 2. Okay, let me think about this. You can only fit 8 of the 17 children present in your van. How many different groups of 8 children can you drive? Well, does order matter? I think in this one, order does not matter. Order does not matter. Because if let's say I choose 7, or no, not 7 children, sorry. We're choosing 8 children out of the 17. Let's say I choose those 8 children in one order. Well, they're all going to climb into my van, and then they're going to go to the zoo. Same, but if I chose those same 8 children in a different order, they'd still all end up at the zoo, So I don't think it really matters what order you chose those 8 children in, as long as they're the same 8 children. I think that's the idea here. So I'm going to go ahead and calculate 8 combinations of 17. I've got, holy crap, 24,310. That is a lot of, what the hell? That doesn't seem right. Am I right? That sounds like some bull crap. Anyway, so we'll use these more in the next section. It's probability now. But still, I think this stuff is interesting. It kind of blows my mind how many different ways there are to do things or choose things, or how many combinations are there. There's way more than you think there are. So all the decisions you make every day, man, you made one choice out of a lot of different possibilities, which kind of makes me nervous in a way. But oh well. Well, okay, one more section and then we'll be home free.